Welcome back. So in part one, we talked about building a confidence interval, and then we finished by talking about how to build a hypothesis test when we're comparing proportions. So let's go back to the same example dealing with college students. We sample students attending various colleges and universities to see how many plan to go to Florida for spring break. 5690 of the 12,931 randomly selected male students indicate they had plans to go, while 1051 of the 3285 randomly selected females indicate intentions to go. Is there a significant difference in the proportions of males and females intending to behave like idiots during spring break? Is there a significant difference in the proportions? And so this is asking us to build a hypothesis test. So we're to find if there is a difference in the proportions of males and females intending to go. Our null hypothesis says there's no difference. Our alternate hypothesis is there is a difference. And this is, if we don't know what direction, this is going to be a two-tailed test. Okay? Another way you could write this is that the proportions are equal, and the alternate is they're not equal. I prefer these ones. Also note the subscripts matter, so the M and the F are male and female, not just 1 and 2. And we're going to indicate that over here. Just give a key for your reader so they can follow along with what you're doing. One or the other. Do not mix and match. Do not use both. So pick one of these ways to write your null hypothesis. Okay, so we are checking our sample size for our males and the number of successes. We are given that, and we know what the sample proportion is. We know our sample size for our females, our successes for females, and our sample proportion. The conditions were met in the confidence interval, so we have met the conditions for a 2 proportion Z test. So let's actually come up with the pooled sample proportion. We're going to use this pooled sample proportion when we're figuring out the standard error. Okay, so this is our pool. N1 P1 hat plus N2 P2 hat over the sum of the samples. So we get 0.4157. With our critical value for, we said 95% confidence interval, so our alpha level will be 0.05, 0.97501, which is 1.96. So look what we do here. Our standard error is pooled, Q hat pooled over N1, P hat pooled, Q hat pooled over N2. This will give us our standard error for our sample distribution. So we get this 0.0096. Next, we calculate our test statistic, which is our z-score, which is our sample proportion, which we know. So we know our information for our test statistic, so we fill it in, 0.4400 minus 0.3199. We are assuming our null hypothesis is that there's no difference. This is why we don't have to write it, and that's over 0.0096. And we get a z-score, this is a z-score, of 12.4723, which should start triggering in your brain. This is some pretty unusual stuff. But let's just go to our calculator, because we can, just to showcase if this is any different. So on our calculator, we are going to run a 2-prop Z test. So we're going to go down to stat tests, and we're going to go to 2-prop Z test. So X1 is 5690 for males, and the sample size was 12,931 for males. The success for females was 1051. Sample size was 3285. Our alternate hypothesis is they are not equal, and then I hit OK. And now let's see. I get my exact same z-score. The p-value is 1.10912 times 10 to the negative 35th, which is incredibly small. We have our sample proportions, our pooled proportion, which is pretty nice to have there, and then our N1 and N2. So what does that lead us to conclude? Well, we're going to draw a picture. We have our sample statistic that's way over here. So the probability that we get this p-value, this is our p-value, is basically 0. So with a probability of essentially 0, we reject the null hypothesis and conclude there is a significant difference in the proportions of males and females intending to be idiotic in Florida for spring break. So here's the mini tab for the testing for two proportions. Ideally, especially on the AP test, they love giving you these printouts so you don't have to rely on your own technology. So what is this saying? Well, here's sample 1, that's our males. This is X1. Here's X2, our N1 and our N2, our P sample for our male and our sample for our female. I don't know why I crossed that. It's calculating the difference, the estimate for the difference, which is our standard error of our pooled. It calculated for us. It gave us our 95% confidence interval, which we saw. It gave us our z-score. And last but not least, our p-value, which was 0. So if you ran this computerized test and you were asked to interpret these values, as long as you know what you're looking for, it gives you everything that you need. So one more problem, and then we're done with Unit 5. Do support groups aid in quitting smoking? A county health department tries an experiment using several hundred volunteers who are planning to use the patch to help them quit smoking. The subjects were randomly divided into two groups. People in Group 1 were given the patch and attended a weekly discussion meeting with counselors and others trying to quit. People in Group 2 also used the patch but did not participate in the counseling groups. After 6 months, 46 of the 143 smokers in Group 1 and 30 out of 151 smokers in Group 2 had successfully stopped smoking. Do these results suggest that such support groups could be an effective way to help people stop smoking? It's a pretty good claim. So let's lay out what we have. In our Group 1, which was patch and group talk, a sample size of 143, a success rate of 46 quitters, and then P1 hat is 0.3217. And 2 of 151, there's only 30 that quit. So P2 hat is 0.1987 or 19.87%. We're interested in determining if the proportion of smokers trying to quit using a nicotine patch and counseling had a greater success rate than those subjects using a nicotine patch alone. So our null hypothesis is there is no difference. Well, we can also say less than or equal to. We only really care about if the difference in the group and patch is greater than 0 than our other group. Now, just quickly check our assumptions and conditions. Smokers are independent, and we're randomly assigned to two groups. The two groups are independent. That's our new condition we have to check. And then N1Q1 is 97, N1P1 is 46, N2Q2, 121, and then 30. All of those are greater than 10. Thus, we have a sufficient success failure to use a normal model. So here's my suggestion to you all. Now, let's just go straight to our calculator. We know what the numbers we're going to have to write out are. Those are on the slides. But I want to run this test. So I'm going to hit Menu, Statistics, Tests, and we're going to do our 2-prop Z test. So Group 1 had 46 successes and a sample size of 143. Group 2 had 30 successes and a sample size of 151. And we are saying that the null hypothesis that P1 is greater than P2, or the difference went up. I'm going to hit OK. And now I get a z-score of 2.4, a p-value of 0.008. Our sample proportions for each is what we found. Our new pooled percentage is right here, and then our sample sizes. Okay, so we have that printout. We're going to utilize that next. So on the notes, we see our pooled is N1P1, N2P2, which is 46 plus 30 over 143 plus 151. That is 2585. That's what we got on the calculator. With our inverse normal score of 0.95, 0, 1, using an alpha level of 0.95, 0.05, because this is a one-tailed test. Now, we come up with our standard error for the difference, which is using the pooled and Q hat pooled for each of these over 143, 151. We get our standard error of 0.0511. Note, this is not in the computer print out, at least not on mine. So now we calculate the z-score. I do need to see this work to show the test statistic. So we take our difference in our proportions divided by our standard error, which we get 2.407, which is what we should. So now we got our z-score, 2.407. Of course, we're going to draw our picture. We've already ran our test. We set up our distribution. We have our centered at 0 with our standard error on there. We get our p-value of 0.008, or our z-score of 2.407 on the standard normal model. Here again is our calculator printout that we ran. And now we just have to come to our conclusion. If the null were true, the probability of getting the difference in proportions as great as 0.123 simply by chance is 0.008. So we are going to reject the null hypothesis. There is sufficient evidence to suggest it is plausible that counseling in concert with the nicotine patch improves the proportion of subjects that quit smoking over those that only use the patch. Since the difference is not 0, we rejected the null. We are now interested in determining the true population difference. So build a confidence interval. So we will create a 95% confidence interval for the difference in population proportions for smoking cessation between those who get counseling and those who did not. The conditions are already met to create a 95% confidence interval with a normal model at 0.123, which is the difference. We came up with our z-score at a 95%, which is 1.96. And then this is our standard error for the difference in our two proportions, which we have to actually calculate. So then we run our confidence interval. You can do this on your calculator. I trust you. And we're going to get 0.002 to 0.2232. So I'm 95% confident that the increase in proportion of people quitting with the counseling over no counseling will fall between 2.3% and 22.3%. That is the increase. Note that 0 is not in our interval, confirming our results from our hypothesis test. This is what we would see from our confidence interval that we built. Here's 0.02%, and here's our upper bound. One last note. When to pool. Really, when do you pool? When to pool? When running a hypothesis test. Confidence intervals, we don't pool. Confidence intervals, we do not pool. And that, ladies and gentlemen, covers everything you need to know about proportions. That concludes Unit 5. We'll do a couple practice problems this week, and then we will be testing shortly. Thank you, guys. See ya.